What's up, Chem friends? Today we're starting week 2 of Unit 5. Unit 5 is on this concept of stoichiometry, but I haven't given you that word yet, and I'm not going to give it to you yet until we get into 4.4, which we'll start into next week. Last week we talked about mole ratios, so we talked about sandwiches and looking at balanced chemical equations. How can we relate the amounts of reactants and products in a chemical equation? Well, it's by using this thing called a mole ratio, which is just the coefficients, looking at the ratio between reactants and products. But I haven't actually told you what a mole is, and that's what we're going to do today. Briefly, I'm going to tell you what a mole is, and then we can use that to find molar mass. So we're going to hit 4.2 and 4.3 today. By the time you walk out of here, I need you to be able to understand what a mole is. And in fact, it's one of the most commonly misunderstood concepts in chemistry. Students don't know what a mole is. They think it's that furry little animal that I have right here, or they think it's that gross growth that people sometimes get with hairs coming out of it. But what I need you to know is that a mole is just like a dozen. It's a counting unit. It's similar to a dozen in that it's a counting unit, but it's different than a dozen in that instead of 12, we're talking about way more. And I believe we went over this when I saw you in the afternoon. So the objectives for today is to understand really what a mole is. So what is a mole? Since atoms are super, super small, like really small, the mole is a good way to count them. Like a dozen. So we could use a dozen to say we have 12 things. So you can look around the room and you're like, I got 12 light bulbs in here, or I've got 12 pencils in here. If you had a mole of pencils, that would definitely cover the earth. The amount of, it wouldn't fit in your house. If you had a mole of pencils, we're talking about 602 sextillion pencils, which is really more pencils or more anything than you can conceive. As I probably mentioned, if you had a mole of pennies and you spent $1,000 a day, every day, 1 day old, 2 days old, 89 days old, all the way up until you were 100 years old, you would have more than 99% of your money left. So a mole of pennies, a mole of dollars, a mole of anything is really tough for us to understand. But because atoms are so small, we use moles, and we would typically represent it in this number because we don't like to carry all of those zeros. A mole is, instead of having 12 things, it's having 6.02 times 10 to the 23rd things. It's having millions and millions and billions and billions of this just one thing. So if you talk about large things like hair clips or flowers or pencils, they're really too big for us to comprehend. But when we talk about moles of atoms, well, because atoms are so small, it's actually much more manageable. And we'll get into that in the next little bit when we talk about molar mass. Since moles are like dozens, we can treat them as equivalency statements. This is an equivalency statement. And so therefore we can write conversion factors. Conversion factors are used in charts. Now, we're not going to convert between individual atoms and moles, but I just want to reinforce the concept of conversion factors. So if this is an equivalency statement, we know a dozen is the same as 12. If I told you to go to the store and get 12 eggs and you came back with a dozen, I won't be mad because they're the exact same thing. So we can write it as a fraction. We can say 1 dozen over 12 eggs, or we can flip that conversion factor over, or we could say 12 eggs over a dozen. Because remember, 12 eggs is the same thing as 1 dozen. So what we're really writing is 1 dozen over 1 dozen, which is just 1, or 12 over 12, which is just 1. Now, likewise with the mole, if 1 mole is 6.02 times 10 to the 23rd, we could write our conversion factor this way, or we could write it this way. And make sure you have these in your guided notes because I'll be looking for them. What do you get when you cut an avocado into 6.02 times 10 to the 23rd pieces? A guacamole. Okay. So what is a mole? It's just a counting unit. And there's a lot of other counting units that you're aware of, like a dozen being 12. Or I don't know if you know this one, but we sell paper by the ream. I know this from The Office. I'm a big Office fan, and a ream of paper is 500 pages. If you have a pair, that means 2. And if you think this screencast goes on for an eon, that's a billion, or 1 times 10 to the 9th. A billion is really more than we can comprehend, or trillion. Like, these numbers are huge, but that's times 10 to the 9th. And Avogadro's number, or a mole, is times 10 to the 23rd. Let me address that. So the scientist who invented the mole, or who discovered the mole, he had a really long name, and his last name was Avogadro. So sometimes when people are talking about moles, they'll just refer to the scientist who developed it. Similar to how Newton, Sir Isaac Newton, gets a lot of things associated with his name, Avogadro gets the mole associated with his name. Okay, yeah, there's a mole. 6.02 times 10 to the 23rd. Way bigger than a billion. It's way bigger than a pair or a ream or a dozen. And we typically use moles when we're talking about atoms because atoms are super small. So in terms of the mole, what I need you to understand is that, sorry, I just got cut off and I don't know what I was saying. We're going to talk about molar mass. So now that we know that a mole is a counting unit, it's just like a way of saying a dozen, but instead of being 12, it's a lot bigger of that counting unit. We can find the mass of a mole, and that's called the molar mass. So what I want you to be able to do is find the molar mass, talk about what the units of molar mass are, and then use molar mass as an equivalency statement. Molar mass as an equivalency statement is something that we're going to be doing. Okay, so what is molar mass? Molar mass is the mass of 1 mole. So in your guided notes where it says molar mass, define it. It's the mass of 1 mole. Now mass is just like, it's a scientific way of saying weight. So if you weigh 150 pounds, that's your weight. Weight is directly related to mass. They're not exactly the same, but they're very similar. That's a physics concept for you. And remember, a mole is just a certain number of atoms. It's 602 sextillion atoms. And I'm never going to quiz you on how many atoms is a mole. The molar mass is just saying, well, if you had a dozen eggs, how much does it weigh? Well, if you had a dozen ostrich eggs, and I don't know if you've ever seen an ostrich egg, but they're giant, versus a dozen chicken's eggs, they'll have different masses. So the molar mass is just the weight of a dozen of eggs. But remember, it's not a dozen. It's not 12. It's 602 sextillion. So the molar mass is going to tell you how many grams 1 mole of a substance weighs. So if you found that 1 mole weighed 20 grams, or 1 dozen, say, weighed 20 grams, then we would say the molar mass, 20 grams, is 1 mole. So if you had 1 mole of something, it would weigh 20 grams, which is super handy for scientists when we're trying to talk about calculations and reactions. So how do we find molar mass? Well, this is just the Braintree periodic table, which you should have. Now, every atom has mass. And the mass, which we went over in that ed puzzle from the snow day, and we also went over back in Unit 1, is determined by its number of protons and its number of neutrons. Remember, protons and neutrons each weigh 1, and electrons weigh basically nothing. So we could figure out the mass by adding up the protons and neutrons, but luckily people have done that for us. So to find molar mass, we're going to look at the mass of the individual atoms and then add them up. So for example, let's say we wanted to find the molar mass of H2O. We've been talking about water a lot, and let's find the mass of it. Well, the atoms that make it up are hydrogen and oxygen. Now we need to find the masses of the individual atoms, but notice we have 2 hydrogens and 1 oxygen. So we'll multiply 2 for hydrogen by its mass, which is listed on the periodic table. Here's hydrogen's mass, and there's oxygen's mass. I'm sure it's too small to see, so I'll tell you that hydrogen's mass is 1.01. That's what it says in that box. And oxygen's mass, in this box, it says 16. So if each hydrogen weighs 1 and each oxygen weighs 16, then what's the mass of the total compound here? Well, we have 2 hydrogens and we have 1 oxygen. So in total, 2.02 comes from hydrogen and 16 comes from oxygen. So the total mass, we would say, is 18 grams. 1 mole of water, if you were to get 602 sextillion atoms of water, it would weigh 18 grams, which is about 18 paper clips. It's like maybe 4 teaspoons of water is a mole, which is wild because if you had a mole of pencils, right, it would cover the earth. But if you had a mole of water, the same number of individual things, but atoms are so small, it only weighs 18 grams. So for the rest of the day, what we're doing is we're practicing our understanding of what is a mole. It's like a dozen. It's a counting unit. If you have a mole of something, you have a certain number of atoms of something, typically atoms, because atoms are really small. And then you're going to practice finding molar mass. So you'll look at how many hydrogens, how many oxygens do you have for water? You've got 2 hydrogens, you've got 1 oxygen. Look at their masses and add them up. Like if I wanted to find my weight, I could put me on the scale. I'm large. But if I was an atom and I couldn't put me on the scale, I could look at the masses of my individual components. So I could figure out the mass of my arms and the mass of my torso and the mass of my legs. So got 2 arms, find the mass of the arms, 2 legs, find the mass of the legs, 1 torso, and add it all together. So yeah, that's what we're doing today. And if you have any questions, please let me know. When we come back, we're going to use molar mass, this right here. Notice it's an equivalency statement, so we can use it to write conversion factors. And that's what we'll be doing in the next screencast. I'll see you then. Thanks for watching. Bye.